Okay, so in the last class we looked at NFA, non-deterministic finite automata, and so you see out of those four machines, we have finite automata, which is DFA, NFA. Then we have next level pushdown automata. Then we have linear bounded automata, and then we have Turing machines, right? So now I talked about DFA, NFA. I talked about regular languages and some of its properties. Now, you can also describe DFA and NFA with another interesting concept known as regular expressions. So I'm going to give you one or two examples about regular expressions. That's all. How, so basically it's kind of, you can think of it as a shorthand for writing big languages, right? In the short form, you can write it down. So I'll show you some examples there. After that, I'm going to go for the next machine, pushdown automata. So pushdown automata, the key difference between DFA, NFA and pushdown automata is that in pushdown automata, we have a memory, stack memory. So you can push something or pop something. Okay. So this is the key difference. And it's a very powerful concept. So use this kind of stack mechanism will allow you to accept languages like A and BN, right? Which you know that A and BN cannot be accepted by DFA or NFA, right? You saw that earlier. So now you can do that. You can accept it with pushdown automata. So I'm going to talk about pushdown automata. I will give you a couple of examples about pushdown automata and a formal description, how to define the language of a pushdown automata and so on. After that, I will go to what is known as context-free grammar or context-free language. So context-free grammar and context-free languages are, so context-free languages are the languages which are accepted by pushdown automata as a machine, right? So pushdown automata accept context-free languages, and each language has a grammar. So context-free languages are generated by context-free grammar. So we are going to talk about context-free grammar. Okay. In general, I will give you the definition of grammar. Then after that, I'm going to talk about regular grammar. Regular grammar generates regular languages. Regular languages are accepted by DFA, NFA, right? And also it can be described in terms of regular expressions. Got it? क्या होने वाला है? Index. ओके, कैरियर टिप्स की जरूरत है, अभी तो टाइम शुरू हो गया है, फिर थोड़ा लेट है हम लोग आज, सो वी कैन स्टार्ट. एंड अगेन थैंक यू टू प्रोफेसर बुश, राइट, फॉर यूजिंग द स्लाइड्स. सो these are very good slides. I think some of you have already obtained it, right? I posted in the lecture folder. You can download all of them. Okay. In fact, if you look at the internet, there are about 40 lectures, but I only picked 10 for you. That's all. Only 10 slides is sufficient for your discrete math course. There's a lot of stuff which maybe when you do a course on practical computer science formally later on, you can look at it. Or if you are over enthusiastic person, you want to learn everything right away, you can look at it. It's there. Anyway. So let me check that everything is okay. I hope. Yeah, I have shared everything. Yes. Audio is there. Yes, fine. So regular expressions describes regular languages. So for example, something like this, A plus B dot C star. What does that mean? A or B and B, connected with C. And star means any number of combinations of that, after that. So basically, this is nothing but A, comma, B, C, and star. Right? So that means this can be nothing but including empty string, then A, then BC, then AA, then ABC, all possible combinations like that, right? This is the language. So you can describe this in this shorthand form, right? This is a regular expression. I'll give you more examples. Formally, there is a recursive definition for it, saying that there are primitive regular expressions phi, lambda, alpha, and given regular expression R1 and R2, there some will be a regular expression, concatenation will be a regular expression, star will be a regular expression, and R1 bracket is a regular expression. Okay, this is a formal kind of definition. we don't have to worry about all this, but rather I will show you a bunch of examples, right? For example, this is a regular expression, right? A plus b dot c star. We just saw that, and dot c plus phi, right? So whenever there is a plus means union kind of thing you can think of, right? So look at this. So we write down, so if R is a regular expression, L of R stands for language of the regular expression. Okay. So this is the notation. So for example, language of A plus B dot C star. We just saw that A plus B dot C star is this language, right? We just saw that how to obtain this language, right, from here. This means A or B and concatenated by C, and then all possible combinations, right, which you will get it. So for primitive regular expression, language of phi is phi, language of lambda is singleton lambda, and language of some element A is singleton A. Okay, this is a, so keeping these definitions in mind, and also these operations. If R1 and R2 are regular expressions, the language of R1 plus R2 is language of R1 union language of R2. Okay, language of concatenation of R1 and R2 is language of R1 concatenation with language of R2. Language R1 star is language of R1 whole star, and language of bracket R1 is language of R1. Okay, these are the basic rules through which we work. So I think now I will show you one or two examples, and that's all about regular expressions. Look at this, A plus B star. So you know it's very intuitive. This writing is very intuitive. You can see that A plus B dot A star means A or B, right? A or B in the initial, followed by any number of A's, right? So you can look at the regular expression here, A plus B followed by A star, any number of A stars, right? So a string is starting with A or B and ending with A's, bunch of A's, right? So now that means how do we compute language? Language of A plus B dot A star is language of whole thing, A plus B calculated by language of A star. By definition, you just saw that. This is same thing as language of A plus B, of the bracketed thing is same thing as language of A plus B, calculated by language of A star. This is nothing but language of A union language of B. We just saw that. Calculated by language of A star. This is A singleton A. This is singleton B. This is singleton A and whole star. So essentially, this is nothing but A union B means A comma B bracket, followed by A star means bunch of A's, right? Lambda, including lambda, empty string, lambda A, and so on, right? So this means when we do the combination, we get this. Okay, so this is how you work out language of any regular expression. Given a regular expression, you can find the language. Given a language, you can also find the regular expression. Okay, just observing it and you can, sort of think. It's quite intuitive, but with some practice, you will get this. So I think there are some assignments I have given in your assignment number 4, I guess, where you can look at these things. I'll show you a couple of more examples. So if regular expression is A plus B star, A plus BB, the language is this. You can just compute. So I'm giving you as an exercise, right? Chai bhi to pini hai sham ki, so you can just go over it, right, and calculate. You can verify that language is so to be this. You have to just apply the formulas, right? All the basic formulas. If regular expression is A star, BB star, B. So you see that all the strings of this form, they were, A or A square or, A square, A4 and so on, those kind of things are there, right? And similarly here, B square, B4 and so on, those things are there, ending with B. So this is nothing but this language, right? So it is very intuitive. By looking at the regular expression, you can write down the language, right? Now, if you put 0 plus 1 star, 0, 0, 0 plus 1 star. So all binary strings of the form which contains substring 0, 0, right? Towards the end, there could be any combination of 0 or 1. Towards the beginning, could be any combination of 0 or 1. I don't care. But 0, 0 should be there, right? That's what it is saying, right? So language, so if regular expression is this, language is all string containing substring 0, 0. Okay? Then this all string without substring 0, 0. So I think I leave it as an exercise for you to look at all these things. हो गया, खत्म, regular expression हो गया. इससे ज़्यादा स्लाइड में देखना नहीं है. और कुछ है मटेरियल, but that's okay. ठीक है ना? So you need to have some basic understanding of regular expressions, right? So next interesting topic, pushdown automata, PDA. Beautiful thing. So look at beautiful thing. So again and again, this is the most important slide of computer science, as I mentioned, right? There are 4 machines, 4 languages, 4 type of grammars. This was done, this classification was done by Noam Chomsky in 1956. Okay. So finite state I talked about. The next machine I am going to talk about is pushdown automata. So what is pushdown automata? I will take this finite automata, and on the finite automata, I will add a stack memory. By the way, there is another beautiful thing. If you take finite automata, add 1 stack memory, you get pushdown automata. If you add 2 stack memory, you get Turing machine. That is also a possibility, you know. So I'm just giving you the connection. If you add two stack memory, that machine is equivalent to Turing machine. Although the description of Turing machine is given in a different way, but they are equivalent in terms of the languages they accept, right? So this is the important result. So finite automata with 1 stack memory is pushdown automata. Finite automata with 2 stack memory is equivalent to a Turing machine. तो मैंने कह तो दिया, इन सबका तो प्रूफ चाहिए. प्रूफ कभी आगे देखना क्लासेस में या कहीं, you know, चाय के कप पे. Anyway, so let us look at pushdown automata. Again, thankful to Professor Bush. I have to say that. Anyway, pushdown automata. So we have an input string and bunch of states, this computational states, and a stack memory. Stack memory means we can only push a symbol or pop a symbol. Push a symbol or pop a symbol, right? Actually, you know, this is just a very simplistic way. We can also push a string or pop a string. A string is operation is also possible in a stack, right? So there is an initial stack symbol, stack head. This is a stack head, or you know, the bottom special symbol appears at time 0. This is $. Here it is Z at the top. Okay, these are just some special symbols. Fine. So here is a description of the how it works. Transition here. You are in a state Q1. After reading symbol A, you are in a state Q1. After reading symbol A, you pop B and push C on the stack. Okay, you read symbol A, whatever is there, you know, on the top, you pop B, B को निकाल लिया, C को डाल दिया, push C. Very simple thing, right? Pop something and push something. Got it? One symbol. Right now we are talking one symbol at a time. Okay, so this is the description. Input symbol, pop symbol, push symbol. 3 kind of symbols, and the state change from one state to the other state. For example, what does that mean? Read A, pop B, push C. Look at the stack content here. B is there. So pop B, B को निकाला, और क्या है? C को डाला, right? Put C, push C on the top. This is the description, right? And you change state from one state Q1 to state another Q2, right? Got it? Push pop business. Another one. What does that mean? You read, just stop and tell me what is happening. Pop nothing, only push C. Pop nothing, push C, right? So this is the stack content. You push C on the top of it. I'm not popping anything, just pushing. So this is push pop business. Yes. What? We can only pop top, huh? No. So basically, later on we'll do whole string business also. You know, I'll show you how the string business is also done. This is where these are very simple situations. These examples are there to understand what is happening, right? How the mechanism works. What does this mean? You pop B and push nothing, right? B को निकाल लिया और कुछ नहीं किया, right? Pop B, push nothing. and change the state from Q1 to Q2, and all those things are there after reading inputs A. What about this? Lambda, lambda. Kuch nahi karna, nothing. No push, no pop, no pop, no push. Actually, it's in this order: no pop, no push. First symbol is pop symbol, second symbol is push symbol. Okay, got it? Well, normally we study pushdown automata which are non-deterministic. Of course, there is deterministic pushdown automata. People study this one, and I think I am going to worry about this only. There are slides of deterministic pushdown automata, but I am not going to look at it. Okay, so PDAs are non-deterministic, so allow non-deterministic transitions. In a state Q1, after receiving symbol A, you have multiple directions of computations to go. Just like non-deterministic finite automata, there are multiple choices to go, right? Either this direction or this direction. In some other state or in some other state, right? Also, we have lambda transitions. Lambda transitions are used for, remember, for changing the state, kind of providing a delay in the system, right? Those kind of properties are there. Now, the first example, watch it very carefully. This is the first example of pushdown automata, right? So now, if I have to accept the language A and Bn with the help of stack, what is the general mechanism? I read first A, then I do what I do? I push. You read another A, push. Read another A, push. जितने भी हैं उतने बार push करते गए, right? And then once you encounter first B, you pop first A. When you encounter second B, you pop second A. When you encounter third B, you pop third B. Third A actually, like that. So you are matching symbols because they are in equal in number. As soon as they match, everything should be matched, right? If the string is A, B, 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 this process will happen. 3 times matching will happen actually, right? First you push A, then you reverse the direction, right? So once you read the first B, pop A. Second B, pop second B. Second A. Then the next B you read and then you pop last A, right? So matching is possible. That is what. So this is what this operation is doing. What? Pushing A, right? Push A any number of times. जितने भी बार A है वो push करेगा. This is the first encounter of B, and then you start popping A, right? So depends on how many A's are there initially. Same number of times B are there, then you can match. So let me see. Let me show you. So this operation puts the A's on the stack, match the B's on the input with A's on the stack, and match found. You finally go to the accepting state, right? When everything is there is nothing to push and pop, right? The stack is empty. You go to the this is how the machine is designed, right? Something which is easy to do. Now look at the example. A, B, B, B. Initial stack content is $. Okay. So what you do? The first operation is just to start. So you go to the Q1 state. You read A. So what you need to do? Push A. Push A. So you can see the stack now. A is there. Second A on the stack. Third A on the stack, right? You are pushing A's on the stack. Next, you are going to encounter first B. So you match B with A and pop, right? Whatever you have put, so one by one you can do the pop business. Pop, 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 and then you are done with this. Basically, you encounter with lambda and then you go to accepting state, right? Got the idea? Very simple idea, right? So A's and B's you are matching. So the language which you could not accept with DFA or NFA can be accepted by pushdown automata because with the help of one stack memory, right? Stack memory is helping you. It's kind of providing you a counter of same number of A's and same number of B's you can match, right? So little bit better than DFA and FA, right? Pushdown automata is better. Dollar is a special symbol, just to identify that now things are done. Stack content may be, dollar is left. And actually, we don't worry about the stack content. It may happen while doing the computations. Remember, this is a non-deterministic automata, right? Non-deterministic push PDA is there. So, but in parallel, multiple computations are going on, right? And so there may be possibility that in one of the path of the computation, we are in the accepting state, right? Input is consumed. All those conditions are there, right? So we do not worry about the stack content. Stack content is just to help you to do the computations. Okay. We do not worry about what is left in the stack content. Okay, so a string is accepted if there is a computation such that all the input is consumed and the last state is the accepting state. Right. Remember, there are multiple paths of computations. At least one of them goes into the accepting state. So we accept the string. Got it? Remember, we do not care about the stack contents at the end of the accepting computation. We do not worry about it. It's just part of computation that is going on. Rejection example, A, B. Why this will be rejected? A को push किया, another A को push किया, B को pop किया, and then we are not in the accepting state, so we are done, somewhere in the middle, right? So A, push, pop, and then we reach to the Q2. Input is finished. We are not in an accepting state, so we reject the string. Got it? Simple है ना PDA. What is lambda? See, this is pop business, this is push business. You don't have to push anything. Lambda is an empty thing, no? No, but no, we cannot do. So basically, there is nothing to push. What I'm saying, the input is consumed. You cannot move any further. Input is consumed, right? Input is consumed completely. I'm not worried. And of course, you see that we are not able to match because see, that matching business is failing there, right? There are more number of A's than B's. So matching business is failing in this construction. This works. Everything works fine as long as matching is done. If the matching is failing, that means if number of A's and number of B's are different, you cannot accept a string, right? No, lambda, see, this is the stack symbol. I'm not worrying about this is not an input symbol. This is a stack content. कहाँ पे lambda डाल रहे हो? No, but lambda क्यों डाले हो? There is no lambda. This is stack symbol. Why you are confused? This is dollar is a stack content. Lambda is not there. Lambda is not there in the stack content. See, input sim. There is a difference between stack content alphabet and remember there is a difference between stack content alphabet and the other alphabet they're using in the in A or B in the language form. Those are different things. Okay, they are different things. I'll give you the formal definition. It will be clear to you when I'll give you the formal definition. Okay. See, this machine is designed to accept A and B and do you agree? Right? So now I cannot change for a specific example. I am not going to change the machine. This machine is going to accept every A and B and right? I am worrying about that. What lambda means what? When the input is consumed, right? Right? And input is not there, right? Input is consumed. Basically, as soon as stack content is dollar basically now. Stack content should be dollar, then you operate this, right? I mean, you think like this. This is just to finish the computation. You need something, right? To finish the computation, you need something, right? To go to the accepting state. Otherwise, because we can make accepting state this, then there will be a problem, right? We need to somehow make accepting state separately, right? Lambda hai nahi na. Again, you are confusing. I am saying the stack content is different than the input alphabet. Input alphabet has lambda, right? Mm-hmm. Lambda means तो कुछ है ही नहीं basically, right? We are not doing anything. तो करना क्यों है मेरे को यही समझना करना क्यों है तुम्हें? तो करना तो कुछ भी कर सकते हो ना. You can design anything. That is up to you. You know that doesn't matter. See, my objective was to construct a machine which can accept A and B and right, and this machine is doing that. That's all, right? Okay. Similarly, so basically A, B we have done. Another example is VVR. So there is any string V of AB combination and the reverse of it. So here again you are going to use the similar mechanisms, similar mechanisms. Somehow you have to guess the middle of this and do the computation, So I leave it as an exercise for you again to look at it, that this machine accepts this, Okay. So if you read, so why there are two things? If you read A, you push A. If you read B, you push B, right? All those pushing business is there. And then this is the, for popping thing, right? So you can design that because whatever you read, you have to again, so whatever you read, you push and then pop the same thing. That's how the reverse will happen, okay? So this is the thing, guess the middle, match, and match found means you go the last one. So I think I'll skip this. This is okay. Okay, so now string business, pushing and popping string. So input symbol is A, pop string W1 and push string W2, right? And you change the state. Now we can define just like that. In DFA and FA we had delta transition, then we have delta star transition function, right? Which works on the strings. Similarly, when we can work on the alphabet, A, B, whatever, and then we can work on the strings. We can define everything on the strings. Pop string, push string, okay? For input symbol A. For example, here, you pop string EB and push string CDF on the top. You can see that. EB is, you pop EB and push CDF, okay? And so, of course, this can be, there are equivalent transitions you can break into push and pop, single stack thing, that is okay. Similarly, this is a machine for accepting same number of A's and same number of B's in any string, Okay, this is different than A and Bn. Remember, this language is different than A and Bn. So this also you can do. I am just skipping this. This is okay. Formal definition again. So we are in a state Q1 after receiving input A, pop W1 and push W2, right? So this can be written in a delta function, delta Q1 A W1 gives you Q2 W2. In case of non-deterministic thing, this will be a set, right? So, for example, if there are two choices, so delta of Q1 A W1 is Q2 W2 and Q3 W3. There are two options, right? This will be a set. Multiple possibilities might be there. So formally, pushdown automata is 7 tuple Q, set of states, input alphabet, gamma is a stack alphabet, delta is the transition function, Q0 is the initial state, Z is the stack start symbol, and F is the set of accepting states. Now, in order to define the language, I will now introduce what is known as ID, Instantaneous Description of the Machine, ID, okay? So ID gives you, machine is doing computation, you take a snap, take a picture of it. So some content will be there, it is in some state, doing something, right? So something like that. We are in the current state Q, remaining input is U, okay? And current stack content is S. Just a picture, some content is left in the stack, okay? Some input is left, some input has been consumed, that is okay, right? And you are in some state. This description is known as ID, instantaneous description of the machine. Okay. So, for example, look at this scenario. This is the machine. So, we are reading head is here. So, B is left over, right? I mean, the input left, whatever is left, B. We are in state Q1, and stack content is AAA dollar. This is one of the ID. So, in any typical configuration, when the computation is going on, you take a snapshot and you are at some, some ID, right? This is one of the ID at one time interval. In the next time interval, it may change. Input will be consumed, one more symbol will be consumed, stack content will be different, and so on. So we can write that. The next one, you see, for example, now we are in state Q2. Stack input is left is BB now, and stack content is AA dollar, right? So ID from one description changes to another description, right? And to another description. So actually, you can start with the initial state ID, when everything is in initial state, and keep on changing the IDs one by one, each time interval. Finally, you go to the accepting state. So all these computations that are done with different IDs, right? They will be helpful in defining the language of the machine. Okay. So this is how you define the language. Let me show you. So we can write it at time 4, it was this, and at time 5, it moves to this, moves to this. Okay. This moves to this. So this is the complete computation starting from start state, and the string is AAA, BBB, one ID, another 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 ID, and finally we're in the final state, Q3, right? So these sequence of IDs describing the complete computation, right? So that means this string is AAA, BBB is accepted by the automata, right? This motivates us that I can define the initial and final ID. So the whole thing can also be written as, starting from this, in 0 or more moves, we arrive at final. In 0 or more moves. So one move will give you one ID change, another move will give you another ID change, another move will give you another ID change, and so on. So language of the pushdown automata is all those strings W, which were initially, right? You are in the start state. This is the stack thing, start symbol, and then finally you are in the stack content is something like this, QF lambda S. Okay. So once in 0 or more moves, so this is how we can define the language of the pushdown automata. So now this belongs to language, A, B, B, B belongs to language because of this description. So A and B and belongs to language. That's all about PDA. Okay, so now, so we talked about finite automata, we talked about regular languages, we talked about pushdown automata. Now I'm going to talk about context-free. Now, languages accepted by pushdown automata are known as context-free languages. And in fact, I'm going to describe the grammar for it. What is grammar? Grammar is there. For any language, you require grammar. So let me show you the grammar. First, we'll talk about context-free languages and context-free grammar. So these are the regular languages, A star, B star, A plus B star. And the bigger set is context-free languages, A and BN. This language is context-free language because this is not accepted by any DFA or NFA. Similarly, this language cannot be accepted by any DFA or NFA. This is context-free language. This is accepted by pushdown automata. So, two descriptions, context-free grammars can describe context-free languages, or pushdown automata is a machine description. Automata and stack, right? So I'm going to now focus on context-free grammar. So grammar express languages, right? English language grammar, sentence, noun, predicate, and blah, 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 right? That is. A cat runs, derivation of this, all these things. So essentially, each grammar, there is a what is known as production rule. Let me show you this. S going to ASB and S going to lambda. S going to ASB, S is known as variable. This S is known as variable. A and B are known as terminal symbols. And this ASB is known as sequence of terminals and variables. ASB, because A and B is there, which is terminal symbols from alphabet, from the alphabet. And capital S is a variable. Okay, here this is known as start variable because S is going to lambda, empty string. Okay, so can you guess what is it is going to generate? Yes. No, S going to ASB hai na. So what will you do? You again apply this rule here. So this will be A B B, and then you use S is equal to lambda. You will get A B B. One language, Then you again use this 3 times. You will get A S B B B. Again use S equal to lambda. Will give you A B B B. Another language, right? Like that, you can generate all strings. So this is, you see, derivation of the string AB. S is going to ASB. You use S going to lambda, you get AB. Derivation of the string AB from the grammar. So this grammar has 2 production rules. First rule, S going to ASB, and the second rule, S going to lambda. These 2 production rules are enough to generate the string AB. What next? You can get AABB. Next, AAABBB. Next, AAAABBBB. A and BN you can generate, right? So language that can be generated by this. So you saw the pushdown automata machine description of this language, and there is a grammar description of this language, right? Grammar is giving you the whole language. You see, AABB, right? So first you use the first production rule, then use again this rule here itself, you get AASBB, and then use S going to lambda. The second one, you will get AABB, right? Like that you can get. Other derivations, 4 A's, 4 B's, then 5 A's, 5 B's, 6 A's, 6 B's, and so on. So language of the grammar is this. So the production rules are this. The language of the grammar is A and BN. And you saw the A and BN cannot be accepted by DFA or NFA, but rather you require a pushdown automata machine. I just showed you the PDA, right? Pushdown automata machine. A convenient notation is starting from the start variable. In 0 or more derivation steps, we arrive at the string AAABBB. Right? Instead of the whole expression, you can write like this. Starting from here, you go here, you go there, you go there, and finally you go there by using the second rule, right? S going to lambda. In general, we write W1 going to Wn in 0 or more derivation. Yeah, so this S going to ASB and S going to lambda, in shorthand form, using this pipe, I can write down S going to ASB and S going to lambda together with pipe notation. That means whenever we write this, S going to ASB and S going to lambda in parallel, right? Pipe means parallel thing, right? Parallelly, there are 2 rules written, okay, in a compact notation. Now, after giving this example, a formal definition for grammar. Grammar consisting of four things. V, set of variables. You saw in the previous example, there was only one variable, S, capital S. Set of terminal symbols, that is small a, small b, small c, those are the set of terminal symbols. S is the start variable. In the previous example, you saw only one start variable, capital S. And P, the set of productions. There were only 2 production rules. S going to ASB and S going to lambda. Only 2 production rules. So context-free grammar. Now we can give you a definition. I gave you the first definition of grammar. So context-free grammar, all productions in P are of the form variable on the left-hand side, and right hand side, left hand side there is single variable, right hand side is a string of variables and terminals, combination of strings and strings of variables and terminals. Okay, then that is known as, so for example, S going to ASB. So ASB a combination of, it's a string of terminal S and the terminal variables A and B, right? So in this context free grammar, S going to ASB pipe lambda, productions are S going to ASB, S going to lambda. Variable, there is only one variable, start variable. Terminals consisting of A comma B, two symbols only, and S is the start variable. Any question? This is kind of straightforward, right? Grammar can generate language, and I'll show you, I have shown you only one example, S going to ASB and S going to lambda. Okay. So language of the grammar, all those strings that you can derive from the start symbol in zero or more derivation. Simple definition, right? Starting from the start symbol in zero or more derivation, all the strings that you can arrive at is nothing but the language of the grammar. Okay, so for the language A and Bn, since there is a derivation from a start symbol in zero or more derivation, we can get A and Bn for any n greater than or equal to 0, right? So context free language, a language L is context free. If there is a context free grammar G with L is equal to LG. I think that's all. This is another example. S going to ASA, BSB, and lambda. So what kind of strings you can get? So bunch of things, So for example, you see AB, BA, S going to ASA, right? And then you use second rule, you will get ABSBA, and then use S is equal to lambda, you get ABBA, which is a palindrome, right? Similarly, if you S going to ASA, use the B wala second rule, then use the first rule, you get that combinations you will get, right? Fine. So this is the language of palindromes of even length you can get. One important thing is that while deriving things, there are two kind of things, left derivation or right derivation. Which variable you use first will give you two kind of derivations. But anyway, I think I'm not going to look at those things. This gives you WWR. So you know that WWR, where W is in AB star, is a context-free language because there is a pushdown automata that accepts it, right? The example that you saw. And another example is this. Okay. I think all these examples are okay. I am not going to look at the derivation order. Maybe I can show you the derivation order. Chhod do. So last thing, regular grammar. So I talked about context-free language and context-free grammar. Regular grammar. So grammar, there are four things: set, V, set of variables, T, set of terminals, S, start symbol, and capital P, set of production rules. These four things are there, right? Now, depending upon the type of production rules you are using, the grammar becomes context-free, context-sensitive, or basically regular. So let me show you the regular business now. First of all, I'll talk about linear grammars. Grammars is at most one variable at the right side of the production rule. So for example, you see in this production rule, there is only one variable on the right hand side. So this is a basically linear grammar. This is also an example of a linear grammar. Right hand side, there is only one variable. All these production rules, left hand side, there is only one variable, and right hand side is a combination of strings and variables. That is nothing but the property of context-free grammar. Context-free grammar, all production rules have a special format. That the left hand side there is only one variable, and right hand side there is a combination of variables and terminals. Got it? Now, this is an example of a non-linear. Why this is non-linear? Anybody can tell? Linear grammar means what? Linear grammar means what? Right hand side there is at most one production rule. So sorry, right hand side there is only one variable, capital A. Right? There is only one variable. If there is only one variable on the right hand side in every production rule, the grammar is linear. Why this is non-linear grammar? There are two variables S. You see, S is appearing twice. So this is an example of a non-linear grammar. Okay. If the right hand side has only one variable in every production rule, then this is a linear grammar. Another linear grammar, right? In this production rule, there is only one variable. In this production rule, there is only one variable, right? This production rule also there is only one variable. If the right hand side has only one variable, grammar is linear grammar. Okay. If there are more variables, A, B, right, capital ones I am talking about, then that is a non-linear grammar. Okay. So again, मेरे को बताओ, what is the definition of context-free grammar? When each production rule has a special format, left hand side there is only one variable, and right hand side a combination of strings and variables. Okay, that is context-free grammar. ये सब definition है, थोड़ा बैठोगे तो आएगी, but I'm just telling you. When there is only one variable on the right hand side in all production rules, the grammar is known as linear grammar. Okay. When there are two variables on the right hand side in each production rule, then the grammar is non-linear grammar. Huh? Huh? S small a, huh? 2 times S and then small a. Huh? No, I'm talking only worrying about the right hand side. Actually, you know, I'm only worrying about the right hand side. Left hand side I'm not worrying about right now, right? In fact, you see, right now we are looking at a very special cases when there is no condition on the left or right. The kind of case that you are talking about, actually those are known as unrestricted grammar. And unrestricted grammar are accepted, you know, generates languages which are accepted by Turing machine, the most powerful machine, you know, so they are most general things. We are looking at special cases right now. Okay. So right linear grammars, all productions of this form. Left hand side there is only one variable, right hand side is string of terminals, or you know, string of terminals and a variable. If this kind of thing is known as right linear, because the variable is on the right hand side. Okay. For example, this is right linear. S is going to ABS and S is going to A. Similarly, this is left linear. Variable is on the left and strings are on the right. BX, you see, BX. And or A is going to, all production rules are of this form. For example, here, you see, A is on the left, right? And then B is there anyway. So now we are ready to define regular grammar. Any right linear or left linear grammar is a regular grammar. Simple. Right? So these are the examples. Left linear, right linear. And regular grammar generates regular languages. So for example, this grammar we generate AB star A. This grammar, this is all in terms of regular expressions I am writing, right? Everything. The languages are I am expressing in terms of regular expressions, you know. That's all I think. इससे ज़्यादा नहीं पढ़ना है बस. So, Adam, so I think we have covered many things, by the way. So, thanks to you for watching. So, now you can look at assignment 4, and I hope you can attack some of the problems. Probably on the last problem, you will not be able to attack history, which is about Turing machine. So Turing machine we are going to cover in the next class. Beautiful thing, right? The ultimate thing. We'll talk about it. Thanks. By the way, if you don't understand or if you have queries, questions, these slides are available in the lecture folder. Please download it and you can go over it. Still, if you have a doubt, as I mentioned, discuss among yourselves or finally you can talk to me, right? Okay.